Well, okay, today our topic our topic today is those microkernel operating systems. I mean, I'm pretty sure that everyone heard this word microkernel. So if I quickly ask you a question, what these are, you can tell me. What's a funk? Jerry, what are the microkernels? Small kernels. And what do we mean by that? What? Network stacks, yes. Oh. And why do we do this? Why do we build microkernels?
For isolation reasons, and then also I think by reducing the CD get a higher
Wow, I agree with you. So that's a pretty good answer. So as I mean, we were talking for the last couple of for the last two lectures, we were saying, okay, the kernels which we run are monolithic, meaning that we boot into a single address space which runs in ring 0. Let me just annotate it here on the slide real quick so we just have a chance to follow what's going on. So the entire kernel, and x86 follows the same kind of thing, runs in ring 0. It bundles together everything from like scheduling, essentially like CPU control, meaning that when we get an interrupt, we make a decision which process runs next. We manage all the processes like as data structures. We manage page tables and or address spaces and page tables. Like we manage all the device drivers or implement all the device drivers in the same address space. Typically today, though, we use something what is called kernel extensions, meaning that they implemented a separate L files which can be loaded later into the kernel, but they still logically run in the same address space. And then we run applications typically in ring 1, or sorry, ring 3. And that's essentially how Linux, well, FreeBSD, I wanted to say Windows and macOS, but Windows and macOS are kind of like, we can classify them as hybrid kernels. So they kind of like microkernels, but without the isolation. So we will come back to it, right? But essentially, this is, let's say, this is a Linux kernel. I mean, for the last, man, I didn't even do anything. Yeah. Oh, back. For the last 2 lectures, I was saying, okay, that's really bad because we started with x86, and we can argue that the original Unix systems were reasonably small, only 10,000 lines of code. They implemented like CPU management, process management, address spaces, and a file system, right? And that's about it. Now we run kernels like Linux, which are 27 million lines of code with tons of subsystems, tons of device drivers. And the idea is that, like, again, we spend so much time figuring out what happens if you find a bug in one of them. But essentially, a bug in any of those subsystems allows the attacker to take control over the entire system, or if impossible, then crush it, some kind of flavor of a denial of service attack, right? And the same for bugs. So like before targeted security attacks, people were just talking about reliability versus security, meaning that accidentally a bug in a device driver will cross the entire kernel and nothing will be able to move forward, right? Okay, cool. So we know that it's bad. If I ask you a question, why is that we're still running monolithic kernels? What's this trajectory? How did we end up using them? It's not on the slide. It's connected like monolithic kernels. Like why? Wow. It's not. So the history of microkernel systems, despite the fact that I didn't have a chance to explain what these are, dates back to almost the same time as monolithic kernels. So the first microkernels showed up late 70s, I would say.
I think the monolithic kernel is more easier to write the code, but the problem is when the size is huge and huge, it's more and more difficult to maintain the code, especially like this kind of old time developer, right? That we need some new or young guys to maintain the kernel. That's so hard for them, I think.
Well, maybe I should ask a question differently. And like, okay, if I let's for a second forget about the question chats. So let's think of like remember that slide with a bunch of systems on the screen. And I said monolithic design where everything runs in a single shared address space is bad. Bad for the sake of like if you have a bug, then everything just stops, right? And we'll come back in a second to the question of why is it we're running them. But if I ask you a question, if you were able to change those designs, what are the alternative options? So how would you structure a kernel to achieve better security and better isolation? Isolation in terms of like fault isolation, when something crosses, and you want to move forward. So like if we were to draw the architecture of a microkernel, what would it be?
I think the microkernel itself directly talk to the hardware, and other service like file system or CPU management or memory management, they are like the subsystem talk to the microkernel.
Correct. So I agree with you. So the microkernel itself, it's pretty much like x86, but without the file system, because you need to manage address spaces, meaning that you have like some code which allows you to manage the page table, and page table represents a process. Within the process, you might be running multiple threads. Well, x86 doesn't have threads, but imagine we have them. So those are like threads of execution, right? And if you want something like a file system, you will execute it as we can call it a process. Execute it as a process, right? And the way, and this is what is somewhat missing in x86, they need to communicate with other processes, right? Because if you want to read a file, so when you hear read a file in x86, you just go into the kernel and it services the read. Here in the microkernel, you will have some abstraction of I draw it as an endpoint, which implements inter-process communication primitive. So essentially, when you send some kind of a message into this endpoint, it reaches the file system runs some kind of a loop and maybe replies with an answer you want to see, right? And so that's one design, right? And clearly we say, look, wow, what did we achieve with this? So a bug in the file system maybe leaves the system without the file system, right? But maybe everything else is still running. And maybe you have some processes which are typical in modern world, like we know them as serverless, for example, serverless. So essentially those are tiny functions, right? So which execute some let's say JPEG encoding. They don't even have any state in the file system. They only simply talk to the network. So the network stack, let's assume maybe this is the network stack runs here, and maybe they communicate through the IPC mechanism to the network stack. Wow, one would imagine where is the device driver running. I would probably also put it as a separate subsystem as a device driver. And then the network subsystem talks through an APC mechanism to a device driver talks to an actual piece of hardware, right? So that's kind of your microkernel. So, but the argument which I'm trying to make is that, if the file system crashes, then at least something else continues running. Like I'll take this argument back in a couple of lectures. But for at least some period of time, people believe that isolation like this introduces reliability. One might disagree with this. That's what I'm saying. I will take it back that if a file system stops running, it's kind of hard to imagine like what else is still running. So it seems that everything else has to be so carefully engineered to make sure that it can either survive across in the file system and keep running, or restart somehow according to some protocol, or does not depend on the file system. But then you ask a question, what if there is a bug in a network stack, right? That's my bug again. And then, well, then even serverless functions stop running because they cannot talk on the network, right? But nevertheless, isolation arguably probably has some impact on security. At least, the bug in the file system does not immediately allow the attacker override parts of the network or steal secrets if you keep them somewhere. I don't know, maybe you have like an SSH key here, which attacker wants to take something along those lines, right? So at least it reduces your attack surface, right? But that's the microkernel organization, right? That's one way to go. And people believe that this is the way to go for a while, and arguably still believe that this is the way to go. But if you think a little bit harder, you might think, okay, if we want to achieve isolation between processes, we might come up with an alternative design as well, not a microkernel, but something what is called an exokernel. Anyone heard of it? How else you can? Exokernels is somewhat similar. Like, exokernels as a concept, they like evolve and were probably deployed as virtual machines and as library kernels. The idea is following. So, like, I just wanted to make sure that we understand the difference between these two design choices. So you also have some kind of a microkernel, although we will call it an exokernel. And instead of like running a separate, let's say, file system or a network stack, what they do is the following. They say, look, we will be running a copy. It's easier to illustrate with a network stack. A copy of a network stack inside each process, right? Why not? Because if you have process 1, process 2, again, think of this serverless where you just like, implement some Lambda function which does something, right? If one of them figures out a bug in a network stack, that's totally fine. This process simply disappears and everything else continues running, right? So you achieve like, and this is similar to a virtual machine, maybe with some custom, maybe lighter kernel, in case you don't want to run a full copy of Linux here, although you arguably can, right? So it's just the trade-off is here, but this also achieves isolation, although, it may be even better so for fault isolation properties, because if you say, look, I run stateless functions, they don't even talk to the file system, right? So essentially, why not?
What exactly the serverless?
Serverless is this idea of how people started deploying lightweight computations on the web or in the cloud, sorry. So the idea is following. So you say, look, in many cases, you observe that instead of like running a process or anything like that in a cloud, you just say, I just want to execute a simple function. Maybe it just re-encodes a JPEG from one format to another, or like create thumbnails, like for a movie, you have a movie file and you want to generate like whatever, a collection. What are those called? Where you like kind of they show you quickly preview of each, not each, or like each part of the movie, right? And they say, look, we don't want to, it reduces your development effort because you say, look, I will be coding against, let's say, my favorite language. I can say Python or let's say Go or something, right? And the cloud provider, instead of like setting up your own VM or anything, they say, well, we'll run your function in isolation by providing a language runtime execution environment. Like imagine Go is running here or something. And it will be so lightweight because we really will run one function that in order to instantiate this VM which runs your function, it will take you much less time compared to like starting a full virtual machine, because Linux boot takes forever on its own, although it can be optimized, but like to boot a Linux probably takes you, wow, again, let's not go into there, like it can be optimized, but those lightweight execution environment, it became the paradigm of serverless computing. So essentially they quickly spawn a bunch of those lightweight virtual machines which each runs a small function. Typically it's just one thread of execution, no multi-threading.
Like an RPC?
It's not like even an RPC, just that, they communicate over the network. They don't have state. They like if you want to send some state, they
Only have input, output.
kind of, yeah. And I mean, like I'm not by far not the best.
But if I want state, what exactly the state?
Well, again, like if you say, look, I want to run a function which takes a movie as an input and creates a list of those thumbnails in some other format. Maybe they all talk to like some kind of a network attached storage where the movie is, which this function reads over the network and then writes back the output. Sometimes it's even smaller, like it can be something like, I don't know, like people do all sorts of things with this. But it seems to, like people figure out that it's easier to scale because it's not at the level of I will start a VM, I will set up a network stack, give it an IP address, then we'll establish communication. But really all I want to do, like just want to run a piece of small code, right? Agree? Make sense? Like lightweight virtual machines, if you like. If you don't want, I'm not insisting on the word serverless, right? Do you get this design? It's very much like a virtual machine. What's the difference between these two, between the microkernel and an hexakernel for my drawing? One of them will work better than another in one scenario. Cool. What do you think? I'll even ask you a question. Yeah, okay, go ahead. No, you think for a second, then we'll discuss.
Since the hexakernel has more isolation, but each process will be relatively larger.
I like your part when you said about where you mentioned isolation. So in fact, I kind of say that the striking difference is that there is no sharing of state here in this hexakernel system at all. In fact, it's not even clear how to talk to a network device because, well, how? Like either you need like two instances of a network interface or something. So here we say that the network stack is running, and maybe each of this guy will even have its own network stack instance, right? But then they all maybe talk to a network device driver, like, and this is where the multiplexing happens, right? So they all talk to a single network device driver talks to a piece of hardware, that's how it's running, right? So, and here there is no sharing whatsoever. As I was saying, not even clear how to access a single piece of hardware. So, like at a high level in hexakernel systems or library operating system, it's easier to build software which is completely isolated. You can solve the problem of accessing a single piece of hardware, like in virtualization, there will be a shared kind of like, we can put it maybe here, a network interface which talks to the hardware, to the network NIC, and those guys will send messages to this NIC. That's one solution, classical virtualization, Zen kind of style. Original hexakernel solution was really to switch this device. So kind of when they switch from one process to another, they kind of like clean the state of this network interface it's running, it has queues, right? But it stops processing the queues of one VM and maybe switches to the queues of another VM, like, or whatever it is, a process in the next kernel system. Well, will it disturb your network traffic? Possibly, but maybe you can come up with a way to make sure that, like, really, like, if the queues are here, like, you flush the state which is in flight and then switch to the next set of queues. Some packets will get lost, right? Or in modern hardware, remember I mentioned that you can virtualize device in hardware itself. It's the single root of SRIV, single root. What is SRIV? Yeah, but essentially it's a technology which allows a single piece of physical hardware expose multiple network interfaces, let's put it this way. And then you can give each of these processes its own network interface, and their hardware does the multiplexing internally, right? So there is a software stack running maybe on some ARM CPU here, tiny operating system itself, and then like essentially exposes multiple like network interface devices. So it's actually it's used in industry. So we'll come back to this idea. So, but you got the point. So you can either do this kind of no sharing whatsoever, isolation, exec-kernel style, or as I was saying, maybe we'll come back and modern like providers use lightweight hypervisors like Firecracker by Amazon and what's on gvisor by Google to kind of implement this idea of this lightweight virtual machines. But today we talking about microkernels. So essentially, like what I wanted to emphasize that microkernels is not the only way to go forward. And like you achieve some degree of isolation, but nevertheless, there will be some sharing in software, like a shared network device driver, and like which will implement multiplexing. But at a high level, arguably, yes, we will talk a little bit in terms of benefits. Like Jerry said, it's easier to reason about the correctness of this microkernel piece itself, but also it seems to be that by isolating stuff for like individual parts of the operating system, file system, network stack, stuff like that, you will achieve better security.
So above these should be the separate processes.
A separate process system?
Yeah.
No, they're kind of like even. We'll like you understand how it works naturally. But microkernel does not really distinguish regular processes, like user level processes, and processes which implement functionality of the operating system kernel here on my screen. They might have like higher priorities in terms of like CPU time. They might have like rights to access the hardware. Like for example, this network device driver has a right to access the network interface. We're going to talk about it. So this process probably doesn't have a right to access this network interface, right? And we will talk about access control and security. Any other questions? So good for now. I will explain how to bootstrap this system, why it makes sense and stuff. But now let's go back to monolithic kernels. So clearly, like this approach at least achieves isolation, and it's not much worse than the monolithic kernel, right? But if I ask you a question, why we ended up running monolithic kernels altogether, what was the? And I said that like people since 70s were trying to, and we were successfully building microkernel systems. So what holds us back? You said it's easier to program because you don't have like, if you do HPC, right, everything has to be sent over the network, right? In some kind of a message.
It's direct.
Like here to even like send like instead of like simply invoking a function, like probably a good example is here in the network stack. If you have a network packet, like maybe let me draw on the screen real quick because it's clean. So if you, for example, in a normal system, right? So if you're running a network stack like TCP/IP, and you have a pointer to the packet, all right? and you said, okay, you did all the processing, you filled in the IP address, stuff like that. At this point, you say, I want to send it to the network device driver or device driver, which implements like level 2 network protocol. You literally just invoke a function, some kind of like IO submit or whatever. And this function essentially, like in a typical modern kernel, since they want to support batching and stuff, they would have like a vector or an array of those packets. So meaning that an element of this array will have a pointer to a packet itself, and this next element will probably have a pointer to a different packet. But roughly speaking, it's still equivalent to just simply invoking a function and passing a pointer across, right? Whether like it's less clear how to do that in a system which the address space is not shared.
Yeah, just like we write program to solve a problem. At the beginning, we just write a big function, and later we like try to like, oh, we should talk about design pattern that or yeah.
Correct. Although, like, again, remember, since we spent some time looking at the Linux kernel at the beginning of this class, it feels that Linux is reasonably, I mean, I cannot say that, okay, it's so clean and modular, but at least the network device drivers are loadable modules, you know, which have a strict discipline of how they register with the kernel, what protocol they follow, how they provide their send and receive interfaces to the kernel. So it's not like a complete mess, but still you do pass pointers across. And maybe, yeah, so I think this, there are two orthogonal things which are at play here. So and one thing is really the programming discipline. So and maybe you're right, so this monolithic mass is a little bit easier to begin with, and probably it's harder to maintain, stuff like that. But that wasn't the reason which was essentially preventing the advance of microkernel systems. What do you think was the reason? It's too expensive, right? So Zhafang says it's just the overhead of crossing isolation boundaries are too expensive, at least on modern CPUs. We'll talk a little bit in a second, but that's really the reason. So that's what I was really ended up running monolithic kernels because they are blazingly fast. And again, as we're moving forward, first of all, we have more silicon on the CPUs, right, which we can use. So it's kind of, I mean, Jared probably knows better, but there is at least like, you know, silicon was super expensive in the first days of, you know, architecture. Now we have a ton of it. We cannot run all of it at once because it eats too much power and it heats everything up too much. But still, you know, we still can run more things enough. But somehow originally, like the isolation abstractions which CPU were providing and like segmentation and paging, they were not designed for those frequent crossings. So essentially it takes you roughly 800 cycles, 400 cycles to cross one way and 400 cycles to cross back, like to return, which is like a lot of cycles because a modern network device driver can process like a packet every 100 cycles, right? So like you have a new packet in a monolithic system, in a monolithic Linux kernel, it takes you 2000 cycles to send a packet from entering the kernel to like leaving it in the network in the queues of the device driver, 2000 cycles. That's going through the network stack. If you run something like a DPDK, data plane development kit, which is like a fast network processing framework, typically user level, it takes you less than 100 cycles per packet, right? So, and then if you say, look, I will be crossing the boundaries of isolated domains, and it will take me like roughly speaking 800 cycles. That's kind of like immediately prohibitive, right? So from 2000, you go to 2800 if it's one crossing, but maybe you cross twice, once into the network stack, once into the hardware, like into the device driver, it's 1600, right? So or in terms of DPDK, it's just simply like prohibitive, right? So it's like 10 times more expensive. And I mean, for a while, we never had any silicon which allowed for this fast crossing of isolation boundaries. arguably, we're kind of approaching that stage where finally we'll come up with the silicon, which is fast enough. And I will spend a couple of lectures in the future, like very soon, covering existing isolation mechanisms which are not page tables or segmentation. And those showed up in like recent ARM and Intel CPUs, so Intel memory protection keys, ARM memory tagging extensions, ARM pointer authentication, extended page table switching with VM Funk on Intel, stuff like that. So right, so there is a chance that actually the hardware designers will give us back the fast isolation boundary switching, and then we will go back to those kind of microkernel systems. And the reason for that is again security. So it's all driven by security and somewhat by reliability as well. But we will come back and I will talk more about why something is more secure than other or not, right? Okay, cool. So we got at least the initial idea of what microkernel should look like. So let me give like a kind of an overview. Like, let's try to figure out how to really build one. So for example, when my team builds a new operating system, everything what we build today is a microkernel, so in one flavor or another. So we don't build monolithic systems. So all of our research work is kind of in this microkernel-ish space, and I will explain why in a second. So okay, so again, microkernels kind of say they came up with this principle of minimality or something. So the idea is that if you can implement something outside of the kernel without significant performance loss, then you should. And there's a couple of reasons here, right? So first of all, the goal, when you keep the microkernel really, really small, as Jerry mentioned, I think, you can reason about the correctness of this code up to the point that you can actually verify it. Like you can build mathematical proofs about it, right? So roughly speaking, a modern microkernel still stays within like roughly 10,000 lines of code. It's same size as x86, right? So x86 is roughly what it was, roughly 10,000 lines of code. It had a file system, but did not have support for threads, did not have support for inter-process communication, right? But roughly speaking, this is where you will be, 10,000 lines of code. If if you're an attacker, if you're like a security team, you say, look, we can actually review the correctness of those 10,000 lines of code. And most likely the microkernel doesn't frequently change. You can start using static analysis. You can start fuzzing this microkernel, or even you can build a mathematical proof, which like essentially captures the intended behavior of this microkernel and proves that what you actually implement matches this behavior, right? So it's all possible today. And that's why this minimality is critical. The moment you double the size, everything becomes much harder. It's much harder to reason whether something is implemented correctly, whether, or even construct a proof, right? So, okay, cool. So in a typical microkernel, so like what the convention is, although arguably you can argue that you can push some or many of those things to the outside of the microkernel, but at least the microkernel implements support for address spaces, meaning that it will help you to construct the page table, or like in a secure manner. The process says, okay, if I allocated a page, I want to map it at a specific address space. The process itself doesn't have an access to the page table because it would be able to like override. If the full control over the page table is exposed to the process, then the process would be able to construct a page table, which gives access to the microkernel itself or other processes, right? So it's kind of protected. So address spaces, obviously threads. So essentially an abstraction of a thread and a context switch, kind of like in x86, when it's time to switch from one thread to another, everything will be saved. The state will be saved, put on some queue, scheduling queue, and then like another thread will be running. It implements inter-process communication mechanism. And the only one we've seen before was a pipe in x86. And well, you can go with a pipe, but microkernels do it slightly different. And there is like two main paradigms, synchronous and asynchronous IPC. I will explain in a second how it works, but just like by at a high level, you can think of it as it's a mechanism which allows you to send messages from one process to another, right? You typically implement some minimal interrupt dispatch, kind of like the interrupt descriptor table is sitting in a microkernel, but actual interrupt processing is not done in a microkernel. So the only interrupt the microkernel processes is which one, typically? Who can guess? Not an exception, interrupt. Who is our hero?
API.
What?
API.
What is API?
Call or something.
No. Interrupts. Interrupts come from devices. For example, from a network card.
Yeah, the network driver. Oh,
Well, network driver, we believe that it can run in user level, and we'll explain in a second how we can put it in user level. But one interrupt makes sense to keep in the microphone. Which one is that?
CPU, time sharing.
Correct, timer interrupt, right? Because the microkernel has to make a decision that it's time to context switch. And that's true. So you can massage it, and people did it in different ways, and you can even move the timer interrupt outside of the microkernel. And scheduling itself outside of a microkernel is the same, maybe because the microkernel can just maintain a queue of runnable processes, or maybe even just listen for a user service to say which process to run next. And simply when interrupt comes, dispatch it to this process saying, okay, look, pick the next process to run, and then you put all the scheduling to user level process as well, which whatever implements fairness, computes who has to run next. But typically the timer interrupt is left in a microkernel, at least for simplicity. But all other interrupts are kind of dispatched. So they dispatched as messages to those user level, if we have a disk driver, so there will be an IPC, and I'll explain in a second how it will work, but essentially will be a message which wakes up a thread running inside the network device driver and processes the interrupt and stuff like that. And finally, so final bit, which is kind of important. So there is also this principle of separating policy and mechanism. So the access control policy lives outside of it. So it's implemented by other services, but the mechanisms to enforce the policy will stay in micro. And I will talk a little bit in a second what it means, what kind of mechanism you need. But roughly speaking, you can imagine if you're running everything as a process, you have to decide which process can access the network interface, right? You say, look, any process can access a network card? Probably not, because then they will step on each other's toes and nothing will be running, right? So you can designate a process and give a right to that process to talk to the network interface, stuff like that, right? But the same for memory, or if you want a process to run on a specific subset of CPUs because you're afraid of time channel attacks, then you say, look, you have a right to run on those CPUs, but maybe no one else in the system has the right to do that, and then you're completely isolated, right? So, but those are the things which go into the microkernel, and everything else runs as a user level process which communicates with the rest of the system through an inter-process communication mechanisms, right? Make sense? Agree? Okay. Again, if you think of x86, the early Unixes were pretty much microkernels without good IPC, without good access control policy. So x86 allows anyone to do anything, right? Processes cannot access device drivers, but for devices, but they write any files, and the file system was the running kernel itself, which deviates from classical microkernels. Okay, slightly. We're back. Okay, cool. So now, the benefits, right? So that's what we were discussing, that you can reason about correctness of those systems, right? And in practice, let me erase what people wanted to build, or when it mattered really. In systems which they call them mixed criticality systems. So my students probably think, okay, the guy says the same words over and over every time we see him. But the idea is the following. So imagine you have a system in which you say, like, I have a microkernel, and I want to somehow split the world in two different parts. One is a mission critical system. Well, maybe, I mean, if it's your car, maybe it steers the wheel somehow, right? Or like you can imagine quickly, in avionics, it's whatever, some actuator or something. And the second part is non-critical. So let's say infotainment. And we see it like on a plane. A tiny example is that we're watching a movie, but somehow at any moment of time, the announcement on the screen can override whatever. The pilot is talking and the movie completely is frozen. And so essentially they can take control over it. And if they run on the same, or maybe a selection of CPUs, but people want some kind of a hard guarantee that this infotainment cannot affect execution of this mission critical part. So for example, if you run a lot of like movies, no matter how hard you try, this thing still runs every 10 milliseconds, it has a chance to like process whatever it needs to process and steer the wheel, right? No matter how much memory this thing allocates, the allocation of memory, which was designated for this system, will never be affected, right? If you think about it, this property, I kind of argue it doesn't exist on Linux, right? And I even maybe mentioned it in one of those possible projects. I said, okay, can we go and reason about Linux containers and Linux kernel and talk about those possible guarantees, whether this hard boundary can be drawn, right? Or like in the system. Because like, even like, imagine the pass in the memory allocated and do something like malloc. Like what prevents this malloc from allocating the last page in a system which was like destined for this mission critical system, and mission critical says, okay, I really need this page like in the next 10 milliseconds or everything will crash. So those guarantees do not exist in systems like Linux, right? But in those microkernels, if you carefully design them, you can construct this core, the minimal core, in such a manner that you can build a strict isolation boundary. That's the main benefit. And so today in production, for example, microkernels will be used for, like, I have not a friend, but I know a person who is a university professor, and he works with a electric car company, like builds one of those supercars. And back in the days, you know, any car would be running like dozens of microcontrollers, like one for each wheel, and it executes the code which steers those wheels or whatever. It does something, and they say, look, it's prohibitively expensive. We just want to put it on a single like generic CPU, but we really need to make sure that we have this hard isolation boundary between those systems. And the guy essentially built them an operating system which runs in this car, and essentially his operating system runs in a car which he drives. That's the level of recursion, right? It's kind of cool. So this is where it is in production. But we'll see, like, we'll take a look at a couple of interesting production examples as well. But that's the point. So essentially, and plus, as I was saying, since this is 10,000 lines of code or less, you can even make an argument that the code which you run here is actually correct. So you can write specification for each system call, and you can say, okay, I expect that when I'm allocating a page, if there is a page still left in the memory allocator, it will be allocated and mapped to this specific address. Nothing else will be changed and stuff like that, right? So now we'll show you later on how to write those specifics. And as we said, okay, isolation of userland helps us to essentially prevent, like, or complicate the exploitation of the system. Okay, so what are the challenges, right? So why is it hard to build a micro? As I was saying, the main kind of challenge in my view is performance, right? So effectively crossing the isolation boundaries is tough. And if we take a look like we kind of like at some point we build a tiny IPC mechanism into the x86 kernel just to measure what it will take. Like even if you execute sysend versus exit instruction, it's 106 cycles. So CPU designers did a great job. So because remember, x86 uses an int x40 instruction, and roughly I think it takes roughly 350 cycles to like process the interrupt. If you build like a minimal system call like hello world, it will take you 350 cycles to do it through this int 40 mechanism, because you traverse the interrupt descriptor table, save everything, restore everything. Sysend versus exit is much faster, so the system call itself is pretty fast. However, if you want to reload the CR3, it roughly takes you like 170 cycles. Even with those stacked TLBs, it takes forever for whatever reason. And so if you do it like twice, because you have two processes running, right, and you like doing kind of a remote invocation style, you enter the kernel once, and then this guy does something, and then it replies. So you do sysend versus exit twice, switch the page table once on the way here and once on the way back, and it at the very minimal puts you like into the neighborhood of 552 cycles, right? It's not great, and as I said, like while by the time you end up saving both the registers, checking writes, also accessing maybe some pages, like again, tag TLB, supposedly the TLB is not in class, so maybe it's not an impact, but like roughly speaking, modern microkernels achieve IPC in the neighborhood of 850 cycles. So not super slow, but not super fast either, right? So this is kind of expensive. But I wanted to like stop for a second and say, okay, if you want to build a system around those messages, how will your IPC mechanism even look like? How would you build it? Like I keep saying IPC for process communication, and I even like showed you some cycles, but like if we were extending x86 with a new system call which implements IPC, what would be even the signatures of those functions? What functions do we want? Like at the high level, the estimation. At a high level, if we have a foo which takes an integer a, and this foo is implemented in another process, how will we go from this process? These are two ones. And if there is a microkernel itself, what's involved? How do we do this?
If you specify which process you want to call,
Yeah.
also the parameters, what function, and then what function, what parameters, and where should the return value be?
Kind of. Like, I want to introduce, remember we had a pipe. In x86, we had a pipe. The only two mechanisms, like you could, let's say, write into this end of a pipe and read from this end of a pipe. And pipe had some capacity to buffer something. So pipe is kind of like a interprocess communication mechanism. It's not great, but it's doable. Let me explain why. So for example, you can say, look, if you're already somehow magically connected by a pipe, I don't know, in x86 it's only from a parent to child, but maybe you get it like from somewhere else, and I will explain in a second. Then it's kind of easy. You say, look, I will create a message format, and it's called marshalling, which says, okay, I will maybe say that I'm trying to invoke a function foo. In practice, it's not because a string, it's an idea of a function. And then maybe you package the argument A, and maybe at this point you're done, you're just simply writing into the buffer. And maybe, you know, like, maybe you have another pipe from which you read, saying, okay, I want to read if it returns something, like it returns an integer, I want to read an integer from this second pipe, right? And then this process, so if this is sender process 1 or caller, this is the receiver process 2, this guy will probably sit here on this pipe doing something like a read, waiting for someone to send a message, right, into a pipe. And essentially, then when it's done, it will just write, like, essentially what happens here, it will read something from a pipe, it will run some kind of a dispatch loop, right? Meaning that it's a thread which constantly tries to read from a pipe. When it reads, it says, okay, what function are you trying to read? So you will have some kind of a switch statement here, and you say case foo, you invoke foo, and then write back the reply, right? It's almost like that in real microkernel systems, except this pipe has a capacity for just, first of all, it's just a single roughly page or like region of memory for which in which there is like finite capacity of registers in which you can write values. It's kind of like a pipe, and you serialize or marshal your arguments, invoke the dispatch loop on the other side, and then wait, like essentially instead of like doing reads and writes, you come up with system calls which are something like send, or like let's say call and reply, meaning that you will send a message into this is typically called an endpoint, and will be waiting for the reply on the same endpoint. And only when you're unblocked by the reply, you will return back into the original caller. That allows you to invoke do a function invocation across two processes, right? The reason it's done this way is that, you know, like, it's arguably very, very fast. I mean, well, at least your marshalling is very fast. You don't have to like there's really no reason to keep multiple messages in a pipe. And if multiple processes like process P1 or P3 try to send into the same endpoint simultaneously, and this server, like a file system, let's say, is already busy, you will just be enqueued, like process P3 will be waiting for this endpoint to become available, and immediately will, like, instead of like reading from this endpoint, it will be something like receive and send kind of message. So it immediately like sends the next message, and then receives sends the message and sends the reply and receives the next message. So in one invocation into the microkernel, right? Is this idea clear? So how to build this IPC mechanisms? I mean, there is like a lot going on, which I kind of tried to skip, but that's one way to do it. And a lot of people agree that that's a meaningful way to do it, to build those IPCs, right? This is reasonable. Notice, however, the following observation, that now, like if you want to implement a file system, you really need to run some kind of a dispatch thread right here, right? Which constantly reads and sends and receives something, right? And those guys who are clients, so let's just imagine it's just a regular process, and this foo is really like a read from a file. They're just more or less regular processes. Just that like the system services are threads, and like they're like kind of like constantly running those dispatch loops, and the rest of the system is more or less normal, right? One way to build it. So this is called synchronous IPC, because roughly speaking, like one thread of execution kind of migrates into another like process synchronously and starts running something, and then gets unblocked on the way back. Notice that in this specific scenario, if this receiver is already waiting on this endpoint, the scheduler is not involved in the IPC. So the system, like, remember if it takes you like 110 cycles to enter, how many 170 cycles to switch page table, then arguably marshalling those arguments would take you another like 20 cycles or something like that, right? But nowhere on the critical path you involve the scheduler. So you don't make a decision about which process runs next. You always immediately unblock the process which is waiting on that, which is ready to receive from this endpoint, right? Okay, cool. That's one design, but still it takes you roughly 850 cycles, which is not fun, right? And so people like said, okay, really want to like, especially if it's a network packet, say send, and every network packet which you send takes you 850 cycles on top of regular IO paths, right? So then people started thinking of how to improve this. So how do you think this can be improved? These synchronous APC mechanisms, which are kind of try to implement remote function invocations between isolated processes, right? And we've seen it in the past already in this class, a better implementation of this IPC, or not better, like faster for certain scenarios. How would you do it? Correct. So you can share memory between them. And then you say, look, they're so nice. I love it. And this is how people were saying all microkernels should be built forever. But then some people started arguing that 850 cycles is not okay on the critical path. And what they came up with is more like what we saw in virtual machines. Right? In virtual machines, in order to communicate efficiently, the client and server uses those synchronous APC to establish a region of shared memory between the two processes. Let's say I will draw them like that. So this will be my process P1. And you can imagine the same kind of scenario. So I can process P2, which implements a file system. Once when they get connected, they talk through a regular synchronous IPC. They say, look, I'm ready to share some of my pages. And I mentioned, we only seen like how we, in this IPC mechanism, when I was throwing those registers, I was saying what it was an integer A. But you can also come up with a message format in which half of those registers are actually kind of pointers to pages. And so you can send a page 1, page 2 across. And when the microkernel sees that you're sending a page, it will map when the receiver is ready to receive a page, it will maybe provide an address into which map this page, right? And so this page gets mapped from like it's shared between two processes. This is how you share a page. In Xen, this mechanism was a little bit convoluted. Remember, there was this grant page, grant tables. So essentially, this guy says, I allow process number 2 to map my page number 16, 77, and 55. And I will somehow identify that guy that he can, right? And in this setup, which is slightly more elegant, you say, look, I'm sending you a page and you receive it in a specific virtual address, and hence establishing like essentially those virtual addresses, those pages donated by the process will establish a region of shared memory. But once this region is established, you say, look, by the way, we might contain some region of metadata which describes this shared region as a ring buffer. And I will be essentially, when I want to send some kind of request to you, I will just add the pointer. I will copy this request here into this buffer, put a pointer, which was like relative to this beginning of the buffer. And then I will put maybe like hundreds of those or dozens of those. And hopefully, meanwhile, you will start running as well. And you will fetch some of those requests from this buffer. And I don't even have to do anything. We're running parallel. If we're lucky, we're running from 2 different CPUs. And if we're not lucky, then we're running on a single CPU, but the operating microkernel context switches us, and we never even have to talk to each other. But if I see that I got to the end of the buffer, which means that probably you were like, the receiver was not expecting to receive anything from me, I will maybe send you some kind of like a synchronous notification, meaning maybe there is still kind of like either like an event style, or maybe there is a thread sleeping on this endpoint saying, I'm waiting on another wake me up and essentially like, because I wasn't running, I wasn't listening, I didn't hear anything from you in a while, but then you can essentially ping and make sure that this guy is woken up and starts picking up messages from this shared ring buffer, right? Why is it faster? Because typically a copy of a small message does not take you 850 cycles, depending on the size of the message. So roughly, let's say to copy 64 bytes, it probably will take you less than 20 bytes to copy into the ring buffer, copy out 20 cycles, right? And so your IPC, I mean, maybe your latency goes up because maybe the context switch, you have to wait for that guy to reply. You cannot immediately wake it up. But, you know, in terms of throughput, it goes up, right? So, and essentially, this is this idea of constructing asynchronous IPC messages, right? And I said that we saw it in virtual machines. And so virtual machines were actually designed to support, like primarily support this asynchronous form of communication, because the running use case was communication with device drivers. Like this IPC channels are established once in a while, and it takes you forever to like negotiate those shared pages. But then once you did, everything goes to the shared ring buffer and everything is kind of fast. And so just make sure that, okay, this is the way to, also the way to build it, right? Okay, good. So we got these two ideas that we can build synchronous and asynchronous APC. I explained how you can build a synchronous APC. This is kind of asynchronous construction. So next, device drivers. So imagine you want to run device drivers as user processes. What do you need for that? What do you think? Oh man, it's on the slide, but you have to still tell me what it is. Like one process suddenly can have access to the device, right? Okay, so how do we even do this? Remember, we talked about device driver, but what does it really mean that it can talk to the device? Do you remember still? If this is physical memory, I mean,
maps range.
correct. So devices are represented by those control regions, which are called bar regions. What is bar? Base address register. Essentially, by like, if this page is mapped into the address space of the device driver process, then by writing into this page, it can essentially signal for like a combination of, like essentially when you, if this is your CPU core, you will have a hierarchy of caches, L1, L2, then L3. I mean, I throw it as a shared one. And then like it kind of has to go to the memory controller, but there is also a PCI controller. And essentially the magic happens here, like somewhere in a caching hierarchy, and it just essentially says, okay, by the way, you're writing into this magical region of memory. So instead of like really sending it to the memory controller, we'll send it as a message on the PCI bus. And it reaches the device, and device says, okay, you're probably asking me to read some memory, but what you do here is that typically what you, in this bar region, you configure a pointer to like a DMA ring buffer, and inside this ring buffer will be pointers to actual kind of like packets that you're trying to send on the wire, right? Agree with this? And another pointer like a doorbell will have something like, okay, the pointer to the current submitted packet, right? Remember? So at a high level, what you need to do is that you need to make sure that this bar region is mapped into the address space of the device, right? However, there's this one interesting problem, which we mentioned. The devices have this capability, DMA, direct memory access. The device itself can essentially, bypassing the CPU, like send something straight into this page, which is, let's say, of course, it's here, right? So it's a physical page, right? So the device can like copy some data directly into the physical page, right? Which creates a problem. So what if this pointer, which this device driver, let's say it's a network device driver, puts a pointer into the page which belongs to a different process. P1, for example. Then device, if this is the page here, like, look, I'm drawing it. What prevents device from writing into this page, overwriting memory of a different process, or maybe even the memory of a microkernel itself? So how do we solve this problem? Do we agree that DMA is there? It goes right into physical memory. So how do we deal with this? Remember? Just wanted to make sure that we all remember. Okay, people who don't do trading systems should answer first. Yes, no?
They directly access the DMA.
What?
I don't know.
No, remember I explained it once, but probably you forgot because it wasn't emphasized strong enough. Remember those IOMMUs, what are those? It's like a page table which sits in front of the device. So essentially, instead of allowing device to access any physical memory, there is a page table which translates, like, essentially, if this is device virtual address space, so maybe device writes into address 0, but since there is a page table implemented by IOMMU, it gets translated to, like, whoever like updates this IOMMU controls where this address 0 is mapped. It's typically done in a kernel. In this specific scenario, you have to come up with where this IOMMU is sitting. It's still probably sitting in a microkernel to make sure that when you, like, there will be a microkernel system call saying, like, okay, I want a device to write into this page. This page, for example, is somewhere in the physical memory. The microkernel checks that this virtual page belongs to this physical page belongs to this process, which requests the reprogramming of IOMMU, and then adds it to the IOMMU, saying that temporarily I allow, like, device address 1, for example, or like first page is mapped to this one, right? And so if the guy tries to submit a pointer which points to another page, it's just not allowed, right? Do you agree? And then this way the device itself can only access the memory of the device driver process, right? So just making sure that we understand how to implement this isolation, right? Agree? Any questions about IOMMUs? IOMMUs are very much like regular page tables, almost kind of bit-to-bit compatibility with the layout, right? Okay, and the second thing, what happens with the interrupts? After all, remember, interrupts are like device occasionally wants to send an interrupt through the interrupt descriptor table. How will you orchestrate? So typically, interrupt handler will be sitting in the kernel itself. But in this example, like, microkernel doesn't know anything about network device. So really, the handler should be sitting somewhere in the network device driver process. So how will we deliver the interrupt there? What can we do? Well, you can, like, as you say, you can remember, like, we do that in virtual machines. So for example, this process can register like some kind of a table with a microkernel and saying, okay, I want to receive interrupt. This is the address of the handler which sits here, and somehow the microkernel remembers that this interrupt, the network interrupt, has to be delivered to this process. So we can implement some kind of an interrupt injection, meaning that we switch to that process, save its state on its current stack, for example, switch execution to the instruction pointer of the handler, start running the handler, right? That's one possible way to do that, and people do that in virtual machines, this interrupt injection, right? But in microkernels, people came up with this idea that, it's kind of more elegant. So you say there will be really an endpoint, and the process which wants to receive an interrupt has to be like waiting to receive something, like essentially implement this receive system call on this endpoint. And essentially, instead of other process sending a message here, the microkernel itself like says, okay, I received the interrupt and I will unblock essentially this process. And it kind of like unifies this scheduling instead of like having separate logic for how to inject interrupts, you just essentially unblock the receivers who were waiting for this interrupt, right? And so essentially your network device driver will have another thread of execution, which essentially will be waiting for this endpoint, which receives messages from the microkernel itself. Although it's more of an implementation detail and it's not like super important, right? But okay, so we got it. So we understand how we can run device drivers in user level, right? By the way, so Linux does support this. So like Linux supports, it's called PCI pass-through. So it allows you to pass through a PCI device into the user process. I don't exactly remember how they virtualize interrupts, but at least for polling devices, they will allow like access to the bar region. And this is when I remember I keep mentioning this magical fast network packet processing framework, which is called DPDK. So it actually runs user level device drivers in Linux and other systems. So essentially the device driver runs inside the process, and then just the whole network processing logic runs in the same process as well. That's why it's very fast. Okay, got it. So finally, access control. So that's kind of tricky. So this microkernel people were not able to set on the answer for how to answer those questions, like which process can access a specific device, or which process can map or unmap a specific like page of memory, stuff like that. Or even like higher level, if we want to do, remember my ideal world, I want to do this strict partitioning, so which means maybe I even want to partition the CPU somehow, or make sure that processes cannot exhaust each other's memory. So how would you implement it at the level of a microkernel? Even if like, think of a microkernel as an x86 minus file system calls plus send and receive, or whatever I was using, send reply, full reply, receive and wait, or a reply and wait system calls for inter-process communication. In x86, there was no control of which process can do what in the system. Like, how would you do that? Like, what's your minimal mechanism to implement access control? Like, just to make it more specific, imagine there is a network interface, like, which has a bar region. Like, obviously, the network device driver has to mmap, like, or mmap this physical page into its own address space, right? So to access it, agree with this? The question is like, how we distinguish this network device driver process from any other process in the system which can try to do the same and become a network interface, or like create an attack which somehow like interferes with the network device. How can we control which pages are accessible by which processes in the system and stuff like that?
Like kernel space versus.
Wow, it's like everything is user space. This is a kernel space. This is a microkernel. But it simply will implement the mmap system call. The question is like how to control whether P1 is allowed to access the bar region or not. Like you need some kind of a decision, like some kind of a key. A key, okay.
Or ID.
Oh, like randomly guessable ID.
No, like if like faucet or network, this kind of service is a range of ID, and the user process will be another range of ID.
Kind of.
Like, for example, in the high speed, as we say, 0 means the user, 1 means the service.
Okay. Have anyone heard the words capabilities? Oh, good. No, tell us how to build them now. What is a capability?
Pointer tells you.
Exactly. So what Jared is saying, imagine you have some kind of a high-level language. You imagine like safety of pointers is enforced, meaning that you cannot make up a pointer. So you maybe can allocate a new pointer on a heap, right? But if it's a pointer to a bar region, then somehow magically it was created when the system was booting, and then you cannot just make it up. But if you have a pointer, then you can do something with this bar region. And this is called a capability access control, right? So it's a little tricky to explain it. And we have just 1 minute, which means probably we should start. We'll come back to it next time. But at a high level, those recent microkernels implement this idea of a pointer, meaning that if you have a pointer, you can access a resource. The very first process which boots in the system will have pointers to everything, maybe from the bootloader, right? And it will have pointers to all the bar regions, all the physical memory in the system. And then the set of resources will get split between the individual processes, right? And you can do this construction differently, but at a high level, the idea is if you have a pointer, you can access the resource. And this pointer is somewhat similar to a key, which you described, right? In the physical world, it's like if I have a key, I have access to a room, right? I can pass a key to you, you can access to the room. Wow, I lost the key. That's not ideal because especially if I fire you and you leave the class, maybe I don't want you to have access to the room. So there's this process of revocation, how to get the keys back. And so it's essentially keys allow you to track to like, what is it? Delegate authority essentially, and ideal at a fine granularity. So if there are like 100 rooms in this building, I will have a key for each room. I will pass it to you, but maybe you're on a seminar and Jared is showing up on Friday, so you will pass a key to him. So it's kind of like local policy decisions. Same with memory. And at some point, me as a central authority may want to say, look, by the way, I will remove the keys, no matter who you gave the keys, like maybe to Jared gave it to Jerry, and then I still get the key back. So it's called recursive revocation. So, okay, we'll come back. So this access control is kind of a cute point. So we'll finish this on Wednesday, and we'll finish microkernels and we'll move on.
Is it the concept of ownership?
Yeah, in a way, it's a concept of ownership of resources. But
I only heard about that word, but I don't know what really that means.
yeah, I mean, it can mean different things depending on the context, to be honest.
They say Rust, right? Rust.
No, not that ownership.
Okay.
Not that. Different ownership. Ownership of resources in the microkernel. Okay, cool. So thank you guys, and I will see you.